All right, today we are going to talk about some divisibility tests. Tests to easily see if certain integers can be divided by certain smaller integers. Some of these a number is divisible by 2 if the last digit is even. You know that an integer is divisible by 3 if you can add up all the digits, and that sum is divisible by 3. You know that a number is divisible by 4 if the remainder, when you divide it by 100, if that's divisible by 4. So basically just looking at the last two digits, as an entire number and seeing if that's divisible by 4. And it's divisible by 5 if it ends in 5 or 0. It's divisible by 6 if it's divisible by 2 and 3, so follow those rules. I skipped 7 for now, but there is a rule for 7. It's divisible by 8 if you basically just look at the last three digits as a single number, and if that's divisible by 8, then the entire number is divisible by 8. And 9 is the same as 3, so if you add up the digits and that's divisible by 9, then the original number is divisible by 9. And you know that it's divisible by 10 if the last digit is 0. And you know that it's divisible by 11 if the sum of the odd position digits, so like the first digit, third, fifth, is equal to the sum of the even positioned digits. And you know that a number is divisible by 12 if it's divisible by 3 and 4, and just follow those rules that are listed above for that. So those are the ones that most people know. So we're going to create a notation just to kind of talk about the general case. So I've got this integer a, and it's going to be represented as an minus 1. That's not multiplication. What that is there is a ones digit, and then a tens digit, and then a hundreds digit. So these are actually the n plus 1 digits of integer a, however many digits it may have. All right, so the value of this number is, you would take the digit that is in this an position and multiply it by 10 to the n, and then a sub n minus 1 times 10 to the n minus 1, all the way down to a sub 0 times 10 to the 0, or just times 1. Okay, so that's how you figure out the value, but when I write it like this, those are the actual digits. It's not multiplication. Those aren't all being multiplied. So we're going to prove any of the divisibility rules using that definition of a. All right. It just makes it easier to write it down, and it makes it easier to notate, because some of them talk about the digits of the number, for example, divisibility by 3. All right, so we know that 10 is congruent to 1 mod 3, right? Because when we divide 10 by 3, we always get a remainder of 1. So if I say that this integer a that has a whole bunch of digits, if I write it out as its value, like I did in the last slide, and I write it mod 3, then all of those 10s are congruent to 1's mod 3, so I can change all of those 10s to 1's. Well, when I multiply by 1 over and over again, it doesn't change the value, so this value of the number is actually congruent to the sum of the digits of that number. Okay? And so if a is divisible by 3, if this is congruent to 0 mod 3, then the sum of the digits is congruent to 0 mod 3, meaning that it's divisible by 3. Okay, so that's just a notation that allows us to apply the divisibility rules. Now let's talk about 7. I learned this one a while ago, and not many people know it. But basically what you do is you double the last digit of the number and subtract it from the rest of the number. And if that's divisible by 7, then the original number is divisible by 7. So basically, I'm taking that number that I talked about before, a sub n minus 1, those being the digits. Well, if I kind of chop off the last digit, okay, so that this new number now ends at what was the tens digit, and now that what was in the tens digit is now in the ones, what was in the hundreds is now in the tens, and then from that number I subtract twice what was in the ones column. If that's divisible by 7, then the original number was divisible by 7. Okay, so let me give you an example of that, like 2282. Okay, what I'm going to do is I'm going to take this 2 that's at the end and double it, and that's going to be 4. And I'm going to subtract that from the rest of this number, which is 228. So 228 minus 4 is 224. Well, I don't know if that's divisible by 7 either, so I will go another step. I will use the 4 that's in the ones column, double that. That's 8. Subtract 8 from this 22 that represents the rest of the number. 22 minus 8 is 14. Well, I know that 14 is divisible by 7. That means that 224 is divisible by 7, and that also means that 2282, or 2282, is divisible by 7. All right, so that's the rule for divisibility by 7. You can prove that if you want to. Try it, and I'm sure there's a proof out there somewhere that if you get stuck, you can kind of follow along. And the last one I want to talk about is divisibility by 13. So basically, if you do the same thing that we did with 7, but instead you multiply the last digit by 9 and subtract it from the rest of the number. If that's divisible by 13, then the original number is divisible by 13. Okay, so basically the same thing we did for 7, but we're taking that last digit and multiplying it by 9 and subtracting it from the rest of the number. So here's an example, 2,639. So basically I take the last digit, which is 9, and if I multiply that by 9, I get 81. Subtract that from 263 and I get 182. I don't know if 182 is divisible by 13, so I will do the same thing again. I'll take the 2 that's at the end, multiply it by 9, that's 18. Subtract that from the rest of the number, which is also 18. That's just a coincidence. And I get 0, and 0 is divisible by 13 evenly. I get 0. So that means 0 is divisible by 13, so 182 is divisible by 13, and that means that my original number, 2,639, is divisible by 13. So a couple of new divisibility rules to add to your collection. We'll use these to show more general, more complicated examples in class tomorrow. So if you have any questions, let me know, and I will see you tomorrow.